data sciences, data analytics sort of work. No neural networks, no GPUs, and then post that, I spent some time in IIT Delhi. I was working with a professor, I wrote a paper there in computer vision, and then started tinkering on a lot of AI ideas. I also ran an AI lab with a bunch of AI talent across India, and that's how Dubverse was born. So Dubverse is a product which is basically a creator product that covers largely video dubbing, which is conversion of any piece of video content from language A to language B, C, D. That covers video subtitles, and that covers text to speech as well. So we've scaled this to about 2 million users at this point in time. It's a global product with some of the largest YouTubers in India, like Beer Biceps, Raj Shamani, etc., are paying users. And we cover a lot of self-serve use cases where essentially what we wanted to do was we wanted to canva the entire experience of generating content, translating content, and that's what we've done with this sort of a product. So this is what we've been up to since last 2 years. Now we've been focusing on building our own models, which is something that I'll cover. Cool. So I think before we go very deep into the speech side, right? I want to cover like what the speech modality looks like. Yeah. So cool. I hope you can see this. So yeah, basically, speech as a modality, I mean, it's not very, very perceptive, right? Because text you understand, whatever you see gets converted in token format, and then you're able to understand how the compression and decompression is happening. But when you talk about speech, while it's very natural that a simple like a biological organ is able to produce sounds and able to perceive sounds, right? But then how does it work sort of mathematically? So if you talk about any piece of a TTA system, so the first piece is that there is some, in very nutshell, right, without going into the deeper levels, there is some form of encoding happening. There is some form of learning happening, which is essentially the synthesizer bit. And there is some form of vocoder, which is basically converting whatever it's learned to a form of an audio representation, right? So this is a very, very high level overview. Next, when we talk about any form of, just to refresh your memory on your audio signal processing days, I'm sure everybody dreaded that, some people liked it, where essentially any piece of audio signal, where you see an amplitude, which is basically in the time domain, gets converted in the frequency domain by using SFT, which is like a Fourier transform, right? So that is what this process is doing, wherein it's converting any piece of audio into specific chunks, and then at the end of the day, what you get is like a MELS spectrogram. Now, whatever form of the transcoding happens, largely happens on this form of a MELS spec, which is something that we'll cover in detail. Cool. So as you would have realized that like text-to-speech in itself as a technology has evolved so much. Remember the days when it used to really feel robotic with each and every word coming out, right? Wherein it's highly it's definitely not of use, has a very limited use case, and that too it's not very production ready, right? But now if you talk about it, we're talking about a landscape where content is, and not just any form of content, even Netflix level content is being produced by AI by using these high level text to speech systems. And I mean, your voice agents and voice bots are so real that it doesn't even feel that it's like a any form of AI, right? So how did this happen? If you really look at it, I mean, while obviously we saw with transformers, there is massive amount of technological breakthrough that happened at a core algorithmic level, which is the transformer itself, 2017. And then the scaling across the last couple of years that OpenAI and others have been doing. Similarly, this kind of parallel has been drawn in speech as well, where the very nature of how do these models learn, which is the entire SSL nature, their self-supervised learning approach has massively improved, where now you don't need to learn on a given piece of corpus, and that doesn't need to be very high quality. So in the sense that like self-supervised learning can essentially kick in with 90% accurate data, and we'll cover that when we talk about what our data strategy, data approach is. The second is powerful generative AI models, where largely we start talking about GANs, which is the first level of that like 32 cross 32 kind of images started to get produced, and now obviously these have progressed to more autoregressive sort of systems. Uh, and diffusion again is a very important component, because when you're talking about any form of temporal coherency, be it in form of image, be it in form of an audio, that needs to be produced with some form of a diffusion model. And obviously, like scaling of compute and data, where we're talking about these earlier when we were relying on ASR systems, then we used to talk about hours of data. That any amount of open source data that used to come in a conference, everybody used to get excited about 20 hours of data, 30 hours of data. But now all of that is so archaic that it feels like Stone Age, and we're talking about scaling of these models on millions of hours of data. So that's what scaling in compute has done to largely text to speech. Cool. Since a lot of you have not worked in the audio, I wouldn't go a lot in depth. But this is the kind of work that we do. We've come up with our own foundational model in speech. It's something that we call Maha TTS for the external world. And this is something that we've created with massive amount of scalability on data sets of diversity, quality, quantity. So I'll cover some of that over here. Uh, Cool. So when you talk about like a text-to-speech system, right? Forget about all of these algorithms. The very basic way to understand is this, like how baby speaks to, how baby learns when he's speaking, right? It's like it starts with very simple words like mama, papa, right? With simple syllables, and then it starts forming a word, like let's say pani, whatever, kursi, something, and then it starts forming sentences. Then it starts forming paragraphs. So essentially, if you look at it, the learning ability of even a human brain is evolving with more and more context. The ability to have different forms of phonemes is what we call, and essentially able to learn that, right? Now, this is what at large in a text-to-speech system we are trying to replicate. Uh, Earlier, these text-to-speech systems were largely based on phonemes. So if you talk about my name as, Varshul, it's V, R, Sh, U, L, like how phonetics, some of us did learn. But currently, I mean, the approach that essentially all of this paradigm has taken is we don't need phonemes per se, because phonemes can be very, very lossy in a certain way. I mean, if you tell you a name, right, then I can just like start to pronounce it, even if I don't know that language in some cases. Why? Because I'm just reading in the letters. I'm not, in my head, I'm not converting that into phonemes. So, which is what these systems have been able to replicate. Uh, yeah, in nutshell, this is what's happening in the pipeline. So you need a lot of text and speech level data. So if let's say hello, how are you is written in English, then the similar corresponding audio needs to be there for that specific said word. So the system essentially is able to learn that mapping. Not just to a level where it's simply pronouncing hello, how are you, but essentially even if you lay out emphasis where hello is always with an excitement, or statistically is 80% with an excitement, then even the system is able to learn that the next time the system has to pronounce hello has to be with a certain amount of excitement, right? So these are the capabilities that have been possible because we prepare some form of a parallel corpora, which is essentially we have a lot of written text and a lot of recorded audios of that corresponding text in multiple languages. Uh, so yeah, just I want to cover a little bit about data. This is I'm not sure who all have recalled this, but this is a slide from a talk by Jan LeCun, which talks about how the entire ability from to go from less supervision to more supervision to less supervision is happening. I mean, essentially, data is practically the way that you would look at it like a cake. Okay, so when you look at a cake, you realize that there is a base structure, which is more of a like the bread essentially, that has the most amount of information, but that not might be the highest quality of information, right? Because that's just the base. Then essentially comes the layering between these between the base. That is the second part. Now the third is where that this gets more exciting, which is what people are calling RLHF, is basically the cherry on the cake. which essentially means that this practically requires very less amount of supervision. So even if you look at a DeepSeek, the way that they are able to exploit more runtime level computation, runtime level inference is basically that, I mean, they move from highly supervision to very less supervision, right? So that is where the entire field is moving. So now let's say in a text to speech sort of a system, we say that we cover, you know what, we cover 10 languages, and now we want to add an 11th language. So you would not need the similar amount of data that you needed in those 10 languages to enable an 11th language, right? So that is what it allows. And I mean, that's how practically we as humans also learn to speak. Like if somebody is speaking, let's say Bengali or Assamese, then you would not categorically know that this is what it means, but you somehow know that it's Bengali. Why? Because it's maybe somehow related to Hindi, and that's what you've learned. So this piece is, I think, very important when we're developing these foundation models, because look, we can't always keep scaling our data pipelines very linearly to the new languages, new use cases, etc. that we need to have, which is why there is a certain component of RL that has to kick in. If not RL, then at least some form of self-supervised learning that basically enables all of these models to perform very well. Yeah, so as of now, we were covering just one component, which is basically the text to speech. But I wanted to zoom out with respect to how this is well suited in a very Gen AI context, how this can be added to direct modalities across the different sort of Gen AI use cases that have been covered. So one of the use cases, I mean, obviously, when we talk about any form of AI deployment, largely we're talking about LLMs, which is largely text, right? But if you really look at it, then the human communication in general is best when it's more speech to speech. When two people are talking, that's the apex of human communication, which is what a lot of these voice bot and voice agents are trying to replicate from sales standpoint, from a customer success standpoint. And that's where you need these, like, speech as a modality very tightly tied into your entire experience of delivering a Gen AI solution and an offering. If you look at, so there are two ways to go about it. The first way is something that we call as cascading approach, which is basically the output of one system is the input to the next system, right? So this is what this piece means. So when you talk about, let's say I ask a question, right? How many people are there in the room? Now that gets converted to a textual format by an ASR system, which is an automatic speech recognition system, which is something that you see every day on a Google Meet or something like that, right? When you press a CC button. Then is essentially that entire intelligence piece that kicks in, which counts and tells how many people are there in the room, and then it comes with an answer of, let's say, 45. Now this 45 is then converted from a text module to a speech module, and then you get an answer of 45. This is the entire sort of stack of a very cascaded approach. But the problem with the cascaded approach is that, I mean, at the end of the day, it's essentially for some form of error compounding that's happening. And practically, if you look at it, 80% of an 80% of an 80% is 51%. Right? So you started by saying that, hey, I have a system, I have a module that's 80% accurate, but then by the end of it, since the nature of this very application is very cascaded, you end up, achieving 50% accuracy. That's as bad as having nothing, in form of any Gen AI application. Which is why you see a lot of this approach moving from a cascaded approach to a end-to-end or a speech native architectures, which is where you realize a lot of these multimodal architectures, a lot of end-to-end architectures are sort of kicking in. And I think OpenAI, on that note, would be the first ones to display that with their GPT-4o and that entire voice module that they had. Even there are two ways to go about it. That A, you do some form of a audio encoder. So now your question is directly getting fed into an LLM. I mean, there is basically you're bypassing the ASR component, which means that there is massive amount of accuracy. And then obviously you have a text-to-speech system, right? So this is one approach. The other approach is that you jointly train everything. And when I say jointly, it's not like a from scratch, sort of a pre-training that's happening. I mean, you train one component and then you convert that to an adapter and then you jointly train some of that. It's basically something like very similar to like welding, if you've seen in mechanical terms, pure mechanical terms. Uh, so this is something that this sort of an approach, I think, is if I'm not wrong, Sarvam is taking this sort of an approach because they release this module separately and then obviously a text to speech separately. This is something that is a completely GPT-4o-ish approach. There's also a couple of more releases if you guys are interested in this. Qt launched something called as Moshi. I'm not sure if someone tested it out in the voice agent space. But that essentially is more of a like a duplex based system, which is kind of what this sort of an architecture is. uh, yeah, so again, I mean, the entire idea of taking a text to speech sort of a system and then combining into your entire gen AI sort of a stack is to very categorically look at what part of the use case that you're serving and where is it fitting in. And obviously there are multiple approaches like I explained over here. Cool. I think this is a little bit from a research standpoint, but I'll still cover. There are a lot of opportunities in on the audio, on the speech domain. One of the things that you can right away test it out with a ChatGPT is that if you give it a negative example of shouting, but saying it in a very telling it a very happy and jolly thing. So in that case, that system would never be able to recognize what the emotion of the audio, or the intent of the audio is, right? Because it categorically falls to the text more than the just the audio, right? So there are a lot of these audio intelligence level sort of features that have to come in. Two people talking, three people talking, we have guys having a Q&A, it's a noisy setting. So that sort of a landscape or soundscape to be covered with audio with LLMs at large is something that's still open, and that a lot of that work will come out. Yeah, RHF, like I explained, is something like rather than talking about voice cloning that a lot of us hear and use, that there is this politician that is being voice cloned, that this celebrity is being voice cloned. But rather than that, can you come up with a very sort of a RHF way to have learning from a sort of a system, uh, and that could unlock very native use cases, like let's say a Hindi in Delhi sounds very different to Hindi in Bihar, right? And that's the same language. And I'm not talking about the dialect even, right? The way that you would pronounce a word, that you would structure out a sentence. So these sort of native use cases get massively unlocked with some form of RLHF, because the need or the amount of data that you require goes down. So as that goes down, then obviously your scalability kicks in better. Uh, Cross-lingual transfers is something that's still not very well solved. Yes, and I think use case around translation, where basically the way that you would want to feel an emotion in, let's say, when you're watching a South Indian movie being dubbed in Hindi, right? I mean, a lot of us feel that gap. There's a native gap that exists, and it's not just the visuals, it's not just the action, etc. It's practically what you want to feel from what the actor is saying from a pure vocalization standpoint. So that, I think, is still has a long way to cover, because there you're trying to map not just a vector space of text and audio, but you're also trying to map a vector space of language A to language B, right? Audio adapters, like I explained in the last slide, that as and when, I mean, Llama 4 is going to come up, right? And then a lot of other open source models that are going to come up. So even DeepSeek for that matter. So can you take that and essentially jointly train some form of an audio adapter into your use case? So these sort of use cases will also get unlocked. Someone in an audio domain having call center sort of a domain data, someone having content related audio data, someone having like a lecture sort of audio data. So can all of that be converted can be sort of jointly trained with some form of an LLM is something that is also one area of opportunity. So we deal with more sort of content generative use cases where basically there is massive need to keep it consistent. It's like what I started my talk in the first minute might not be very consistent in the 10th minute. But if I'm a good orator, then I can maintain that for good 60 minutes, right? So this sort of a system is something, I mean, that that boils down to the very fundamental properties of these models as well. So one of the things that we are massively focused on is context window. So the difference between taking two 10-second patches and then combining them versus generating a one long 20-second sort of a context is the difference in the delivery or the quality and the accuracy that my enterprise pays me for, right? So these are some of the things that we are working at a very fundamental level. Yeah, sorry. Right, right. Yeah, no, that's definitely a problem, and that's a problem at two levels. One is just the very setup of that data. The domain of the data is not something that the model has seen. Let's say people, you having a call in a standing in the market. I mean, that's not something that the model would have seen, right? So that is the problem. The other problem is that there is a lot of upsampling and downsampling happening as well, because the call is generally, I think, as is at 8 kilohertz, right? But these models are trained even higher, 16 kilohertz, etc. So when you're trying to fit that data into these models, then you're doing some form of upsampling, which might not be very accurate. So again, some form of cascading is happening. So hence, you would not get the best of results in this sort of a setting. But what we've seen is off-the-shelf models like Whisper, OpenAI's Whisper, etc. They work decently well, provided it's in English. If it's Indian languages, then you're going to have a hard time. So yeah, yeah. Just play some of them.
I bought a vacuum cleaner 6 months ago, and so far all it's been doing is gathering dust.
Yeah. So I mean, now essentially, just keep playing some of them. These speakers are able to be so emotive that they can even generate a laugh, and we don't have to induce a laugh. You don't have to tell that, hey, you need to laugh after the fourth word, because you can't do that as a user, right? So the
I'm
model. Yeah.
just I'm trying to like process it all, but it's like I'm happy and sad and everything in between.
Yeah, maybe the fearful one, I think that's in Hindi. This one.
कौन है वहाँ? देखो, मैं मजाक नहीं कर रही. अगर अगर कोई है तो सामने आओ.
So yeah, I mean, it's able to induce all of those emotions that you practically feels like it's a human. By the way, it's not human. All of this is AI, and this is something that we've been able to unlock because, like I said, that one of the things that we work on was is long context models. So these sort of models is something that we've trained of our own. I mean, the pipeline that I explained, some of our work is out in open source as well. That's not very updated, but you can still check it out. Earlier, I mean, the journey went from that we released our first set of models, started working with some community. We did short context model. This was about, I think, 10 seconds, and then one of our work also went live on Netflix. If you've seen that series of IC814 Kandahar hijack, we've powered ex-politician's voice, which is now no more, and now the production house wanted his voice, so we created a voice clone version, and then they went live with that. Then we started working on long context models so that they can maintain that coherency, consistency, etc. That went live on for audiobooks, and now we are working on a lot of emotional controls and context, which you saw in the slides. Uh, yeah, so I mean, on that note, we've trained these models. We've sort of spent 100,000 GPU hours How I get it as a small startup is maybe a talk of another day, and I might not reveal all my secrets. But this model is something that's been practically trained, from scratch. It's covers about 16 languages, works really well on certain domains. This is meant for enterprise, so you would not see a lot of noise about Dubverse doing a lot of this. Uh, and yeah, this is our little machine. We call it Tomahawk. This is in our office. I mean, this batches about 5 to 8% of our workloads, but then the very ability of not renting out a space of sorry like a cloud and having of your own is something that I consider as a big milestone in our journey. So we did that sometime 6 months back, and I mean it's mostly of use. So that ways we end up saving a lot that we end up spending on foreign clouds for GPUs. Yeah. So yeah, that's about us. That's about it. Thank you. Thanks for being a patient audience.
Thank you, Ashul. The question and answer session, if we can take it outside, if you don't mind.
Yeah,
we'll
yeah,
have
please. Yeah, happy to catch me outside. I'm still here for some time. Happy to talk about anything audio, anything like startups, creator space, and everything. So yeah, thanks everyone.